to join you at this premier gathering on forecasting. In the past few days, numerous domain experts have explored many cutting-edge algorithms. We also confront the pressing challenges of real-world, non-stationary time series. Forecasting in dynamic environment, we have come to recognize that the real-world forecasting isn't just about developing learning algorithms, but rather an integration of forecasting mechanics with operation research strategies. Today, drawing our latest findings in challenges technologies in cloud research, I'll try to show how time resources forecasting technology can be applied to optimize resource management problems in practical and large-scale settings. Today, my report is divided into 4 parts. First, I will introduce the overarching concept of cloud resource operations and management and the pivotal role that demand forecasting plays within it. Second, I will provide a landscape overview of demand forecasting in cloud computing. Third, I will describe the forecasting technique we actually employ, which we call it as the mixture of increasing determinacy. Finally, I will discuss the enhancements we have made to our forecasting mechanics to better handle uncertainty in practical deployments. In today's fast-moving digital landscape, the demand for cloud resource is growing at a very high speed. For instance, the large language models often rely on cloud environments for both training and inference. Therefore, building world-class resource management capacity is a cornerstone that underpins accelerated customer success and sustainable business expansion. This mission is twofold. First, to deliver high service level agreements and quality of service on the public cloud that our customers can rely on around the clock. And second, to do so with an compromising focus on operational efficiency. By continuously monitoring performance, enforcing compliance with service level objectives, and upgrading our infrastructure, we not only safeguard seamless user experience, but also drive down costs. In short, efficiently cloud resources operations and management enable us to balance up compromising queues and service level with cost-effective resource utilization. The first one is the cloud resources operations begin with demand specification. Cloud resource demand typically refers to the requirements of CPU cores, memory, and storage capacity, and the number of GPU or NPU cards across different server types or hardware generations. Cloud carriers as us offers a variety of servers, some optimized for high CPU cloud frequency, some for large memory or storage, and the other equipped with GPUs or NPUs to accelerate specific business, such as large model training or inference. Each available in multiple hardware generations, different countries and different regions. Frontline managers consult with clients to understand their cloud workloads and compute resource needs. Then combine the insights with historical utilization data to forecast resource consumption over the upcoming period. This process is known as demand forecasting. Then, in this era of rapid digitalization and explosive growth in cloud services, customers' compute requirements and overall demand for cloud resources rise in tandem. This compels cloud service providers to adapt proactively to their clients' increasing needs by provisioning additional capacity in a timely or periodic manner, thereby avoiding service interruptions that could disrupt customers' business. This process is known as the capacity expansion. A common practice is to start resource provisioning as soon as utilization approaches to a predefined threshold to ensure continuity. This threshold, marked by the red one, is often referred as the run-out and sell-out watermark. The expansion itself follows a stages run-out, and our goal is that by the time that provisioning completes, these newly expanded resources seamlessly absorb incoming demand. Throughout this workflow, accurate demand forecasting plays a very important role. By predicting future utilization incomes where to set the sell-out threshold and determines precisely how much capacity should be expended during each expansion cycle. Next, in the service orchestration, we offer a variety of services that facilitates the resource management of customers' business. For example, we offer container-centric environment, allow resource scales primarily driven by platforms that manage container life cycles, scattering, and network to ensure resilient, scalable application delivered through Kubernetes. And finally, as cloud infrastructure evolves, organizations frequently encounter that underutilization or retired legacy on-premise servers that still hold residual value. The legacy reutilization phrase focuses on decisions that the legacy assess cost-benefit trade-offs to determine whether and how to dispose them to maximize their resident value within involved cloud ecosystems. There are three distinct pathways: promotion, recuperation, and decommissioning. This phase also requires demand forecasting techniques, since accurate forecasts tell us whether or not a given resource should be classified as declining asset and forwarded into the legacy reutilization decision-making process. From an academic perspective, cloud resource management can be viewed as part of the supply chain and inventory management domain. I will now briefly visit the key element of inventory management problem. We expect to know, under the constraints of specific replenishment costs, lead times, and inventory limits, we aim to minimize total operational costs for uncertain demand through periodical inventory reviews and resource replenishment over a future time horizon. For cloud computing, more precisely, it is formed as a rental-based inventory management problem. Specifically, customers do not directly buy or purchase servers as traditional inventory management, as shown in the left figure. Once a customer's anticipated workload completes, such as an online event or a model training job finished, the cloud resources occupied by those instances are released. Another distinction is that the cloud computing resources are virtualized, which gives rise to a virtual to physical mapping between customer-allocated resources and the underlying physical servers. The mapping challenge is formulated as an online cloud resource scheduling problem. Cloud resource scheduling often reduces to a multidimensional bin packing problem. in which the virtual machines are application counters with device resource demands, for example, CPU cores, memories, storage, GPU or NPU topology, and network bandwidth. These must be assigned to a finite set of physical hosts. The goal is to maximize infrastructure utilization and minimize operational costs by packing as many workloads as possible into each server without violating capacity constraints or topology constraints. Unlike classical bin packing, cloud environments introduce heterogeneous in both host capacities and workload requirements, as well as the dynamic arrival and departure of tasks. Moreover, additional objectives such as energy efficiency, load balance, topology-aware, and SLA guarantees compound the scheduling challenge. Because the problem is NP-hard, practical solutions rely on heuristic or some other algorithm, often augmented by predictive modeling to anticipate resource contention and depth allocation in real time. The cost optimization objective function in inventory management comprises three key components: replacement costs, holding costs, and stock out costs. Demand forecasting plays a vital role because both holding costs and stock out costs are intrinsically tied to forecast accuracy. Under given lead times and replenishment cycles, overestimation of demand results in excess inventory that incurs additional holding costs such as storage space and maintenance. Conversely, underestimation leading to premature stockouts, especially when the next replacement cycle isn't immediately available, creates supply gaps that translate into lost skills and reputational damage, quantified as stock-out costs. While the ideal is a just-in-time zero inventory model represents an ideal operational paradigm, real-world implementations must account for fixed ordering costs for replenishment. Consequently, the replenishment cycle must be jointly optimized as part of the overall solution. In a word, demand forecasting is a critical component of holding stock-out cost modeling. Same to cloud computing. Since certain resources like virtual machines and containers operate through virtual physical mapping layers, our demand forecasting framework first predicts virtual resources requirements before undergoing a subsequent conversion phase to physical allocations. But in this presentation, we'll focus specifically on virtual resource demand prediction. Cloud computing resources encompass not only servers, but also numerous auxiliary facilities. While typically imperceptible to end users, these infrastructure constitute essential components for ultimately delivering computational resources. In the following section, I will systematically articulate the complete resource provisioning chain as well as the demand forecasting landscape. Cloud computing is a capital-intensive industry that involves a vast array of resources beyond just servers. Servers must be housed in rack-mounted enclosures to enable network connectivity. These racks require development in equipment rules with power, cooling, and enclosed cabinet modules. And such equipment rules must be situated within data centers, needing corresponding land allocations building construction, and power supply provisions. They form together a cloud service delivery chain where precise operational management is required for each resource to achieve desired outcomes. Customers can only be aware of virtual resource while it is launching backward reasoning from the end supply. Inaccurate operations can trigger a cascading chain reaction, amplifying losses. Over the past few days, leading researchers in time series forecasting have shared state-of-the-art advances, ranging from classical statistic models to transformer-based or large language model-based forecasters, and even domain-specific foundation models. Today, I would like to move a spotlight to forecasting methodology. Using cloud capacity demand forecasting as a practical example, I will discuss how we can improve algorithm performance for time series forecasting, especially for non-stationary series, by improving the forecasting mechanics. In real-world applications, many forecasting targets are hierarchical and is multi-granular. Basically, forecasting of hierarchical generally data can be broadly divided into two directions: the macro-level coarse-grained forecasting and the micro-level fine-grained forecasting. Take a practical business as cloud resource operations scenarios as example. There are four hierarchical aspects with regard to the target time series data we want to forecast. As previously mentioned, cloud carriers offer a variety of types of servers here: advanced CPUs, large memory or GPU or NPU equipped with different hardware generations called flavor type, the green one. Each flavor type comprises multiple flavor IDs, which represent distinct virtual machine models within the same hardware or server category, but with varying resource allocations. Additionally, our cloud resources are global distributed. To minimize network latency, we develop servers in multiple countries and regions, with some notations hosting servers across multiple geographic areas. These are designed as regions, the orange one. To enhance service availability, resources within each region are partitioned into availability zones where power domains are physically isolated. Customers can require different kinds of flavor types, flavor IDs, regions, and available zones. Time series at different levels of granularity often exhibit distinct stationary or non-stationary, and consequently varying levels of forecasting difficulty. Take the granularities of types as example. Consider customer A's demand for a server of flavor type X, which comprise two specific variants, flavor ID X1 and flavor ID X2. Customer A switches between these two variants based on price and available capacity, yet the aggregate demand for flavor type X remains relatively constant. Forecasting at the flavor type level therefore entails smaller fluctuations than at the individual variant level X1 or X2, making it inherently more stable or easier to predict. As another example, small and medium-sized customers each display highly valid individual demand profiles over time. However, when these customers are treated as a single population, their total demand evolves far more smoothly. This smoothing effect arises from the statistical principle that Aggregating multiple independent or weakly correlated time series reduces relative variance, often referred to as the law of large numbers, thereby producing a more stable, low-variance aggregated series. If you refer all customers in a country as a whole, then the sum of their demand can be very stable in terms of their increasing speed. Of course, this does not imply that coarser granularity naturally entails lower variations and thus better predictability. Note that each dimension is independent, and the microscopic do not necessarily exhibit less determinacy. That's why decomposition can always help identify components with differing predictability. In fact, some individual long-time subscription customers exhibit extremely stable usage patterns, making their forecasts more reliable than those of aggregates mixture with other more valid customers. In addition to considering microscopic versus microscopic granularity across target time series data, such as geography, cataloging, population, and time, we further distinguish models by their applicability. Interpretable models tailored to microscopic determinism and purely data-driven models designed for microscopic stochastic fluctuations. Interpretable models or algorithms are typically constructed on micro-level semantically meaningful features, whereas black box approaches merely fit the data without relying on features that are both high-level and amenable to explicit rule-based interpretation, at least not that explicit. For example, we know that attention is all we need to formulate a relationship between one and other tokens, and transformations can be treated as state superpositions, but we still do not know about what the state tensor values stand for, nor can we reduce them to explainable logical rules. They are entirely microscopic in nature. In comparison, the season trend loss STL decomposition model offers a structured framework for time series analysis by explicitly separating a signal into trend, seasonal, and resultant components. Its interpretability stems from its deterministic and mathematically transparent decomposition process, which contrasts with purely data-driven black box method. The trend component captures long-term movements, often reflecting underlying structural shifts or persistent growing patterns, while the seasonal component isolates period fluctuations tied to fixed intervals, for example, daily, monthly, or yearly cycles. The residual representation noise and irregular variations can be further applied to detect anomalies or stochastic influences. I'll explain why context-specific adaptation is crucial for micro and macro perspectives. Drawing an analogy from physics, modern physics theoretical research has developed two major branches: the cosmology, Newton mechanics, or the relativity, which study evolution of the microscopic universe, while quantum mechanics, which examines microscopic particulars and quantum dynamics. If we want to predict the future behavior of a star, galaxy, or galaxy cluster, we prefer cosmology and model it using the lambda called dark matter framework. If we aim to understand the behavior of a particle or the evolution of a quantum system, we turn to quantum mechanics and solve it via Feynman path integrals. The incompatibilities arises from the fundamental scale-dependent government principles and mathematical irreconcilabilities. Cosmological models fundamentally rely on general relativity's smooth space-time continuum, where gravity governs cosmos scales and matter's distributions are treated as continuous density fields. In stark contrast, quantum mechanics operates through non-computing operators and path integrals that inherently embody discrete Planck-scale physics and non-local entanglement. This framework employs fundamentally incompatible mathematical representations. Attempting to interchange their methodologies would violate their respective foundational principles. The physical analogy offers critical insights for granularity-aware time series forecasting, just as cosmology and quantum tools are irreplaceable for their respective scales and their underlying evolution principles. Forecasting models must adapt to temporal data resolution and their evolution principle constraints. At macro scales, for example, yearly incoming trends, global matters, or like specular trends or low-frequency cycle align with lambda cold dark matters, coarse-grained modeling philosophy. Conversely, micro-scale demand quantum mechanics like precision. Techniques like wavelet transform or high-frequency noise modeling become essential to resolve abrupt phase transitions or stochastic validations. Crucially, misapplied methodologies across granularities induces errors. A microeconomic model forced onto thick data would over-smooth high-frequency signals, while a noise-sensitive, quantum-inspired approach applied to climate data would overfit long-term dependencies. This underscores granularity as first-class modeling dimension, necessary hierarchical matter architecture that adaptively adjusts to observed resolution regimes. In modern physics, string theory, a research domain attempting to unify macroscopic relativity with microscopic quantum mechanics, has emerged as a prominent field of study. What if string theories, or the so-called theory of everything, were ever successfully developed? Would it can certainly become the sole method for solving practical problems? I think the answer is negative. To unify these two fundamental theories, string theories dimensional and consequently its computational complexity must inherently be extremely high. When confronting real-world problems and practical computation constraints, alternatives model would likely remain preferable. This parallels how we refrain from applying relativity theories to model low-velocity object motions. Even when simulation galaxy-scale system with quantum-level precision, a two-phase approach would likely prevail. First, employing Newton mechanics and relativity to resolve microscopic geometric evolution, and then analyze quantum mechanics to derive microscopic particle dynamics based on the known macroscopic solution. Actually, the micro and micro classification of models merely borrow the semantic context of physical terminology. At its core, its distinction falls on whether the modeling possesses interruptible and logical deterministic properties. These methods employ distinct explanatory approaches and learning mechanics for data processing, consequently requiring different pre-processing procedures. Among the models of time series forecasting, Season tree laws, ARIMA, and Bayes approaches represent interpretable frameworks designed for micro-level deterministic problem. In contrast, techniques of signal processing, like ensemble-imperial mode decomposition, deep neural network, and large language model, constitute a distinct category. They operate through complex fitting mechanics to characterize micro-level numeric transformations while lack explicit logical interpretability. I'll explain why I prefer deep neural network or large language model being microscopic model. For both transformer-based large language models and their applied to time series forecasting, although powerful to handle micro-level big time series data, the reason why I prefer to place them on the microscopic level is their mechanics is similar to quantum mechanics. From a quantitative view, physical-inspired perspective, we can draw these loose analogies between transformer mechanics and quantum mechanics. The first, the superposition. Each input embedding is a real value state tensor blending multiple latent features, and the linear projections in attention and feed-forward layers distribute and recombine these features components, much like expressing a quantum state in different bases, except for lacking complex amplitude and phase information. The second, measurement-like weighting. The dot product of query and key tensors is normalized by softmax into non-analytic sum-to-one weights that highlights the most relevant value tensors. Analogies to quantum measurements probabilities except for no irreducible collapse or projection onto a single basic state. Third, multi-basis projections. Multi-head attention applies independent linear maps to the same input, projecting it into several learned subsequents in parallel. Measuring a quantum state in multiple bases simultaneously, except for the absence of orthogonality constraints and any collapse-induced state change. The last, iterative transformation, is stacking layers of attention feed-forward transformations, residue connectors, and normalizations progressively refined the high-dimensional representation. Reminiscent of applying sequential involution operators in quantum mechanics, except for non-unitary, irrelevable operations that do not conserve amplitude norms. Taken all mentioned together, these analogies provide intuitive bridge between transformer operations and the spirit of quantum mechanics. Therefore, transformer-based large models and, in fact, all deep neural networks closely mirror quantum systems. With a transformer, each token behaves like a superposition of the latent semantic state tensors. Through successive untextual superpositions, it gradually collapses into a more sharply defined semantic probability. There are no overarching, rule-based laws, only microscopic accumulation and convergence. It remains difficult to formalize exactly why these transformations occur as they do. Yet, empirically, they collapse through layered attentions and decoding. This very mechanics underlines the hallucinations seen in large models. Since their operation isn't governed by explicit logical rules, the challenge is even more pronounced for time series large models than for language models, because the superposition to collapse dynamics of numbers time recent values converges more slowly and exhibit far greater complexity. Let me illustrate with a concrete example. When a transformer or large language model decodes the sentences and predicts the last token, international symphony on forecasting is a premier gathering on what? The preceding tokens, international symphony on forecasting and gathering, have already provided strong semantic context indicating a domain of predictive analytic conference. This makes the model highly likely to converge on forecasting after all. Even if the correct answer were prediction, the semantic deviations would remain minimal, with little impact on subsequent responses or decisions based on the statement. However, even using the same transformer mechanics, time series forecasting operates differently. Unlike a natural language where tokens exhibit inherent semantic or logical coherence, temporal values only possess number of correlations. These correlations may be strong, for example, the causal patterns, but it can also be weak, for example, highly stochastic. Low correlation values. Consequently, even with abundant tokens, the model often struggles to converge towards well-defined semantics, resulting in prediction confidence intervals that may remain rather wide, leading to a high deviation with regard to accuracy. If there is no many historical data for transformer-based model to train, there is another microscopic technique called complete ensemble empirical mode decomposition with adaptive noise. It is an advanced adaptive signal decomposition technique that extends the conventional example impairment mode decomposition by incorporating fully adaptive noise control and complete example strategies. As a purely data-driven approach, CEMDA decomposes complex non-stationary time series into a collection of intrinsic mode functions through an iteratively shifting process that automatically adapts to the local characteristics of the signal. Unlike traditional frontiers of wavelet transforms that rely on predefined basis functions, the intrinsic mode functions generated by Kiden emerge purely from the data's inherent, making them particularly effective for analyzing signals with stochastic, nonlinear, and non-stationary properties. However, this data-driven nature also introduces challenges in interpretation. While lower frequency intermode functions often correspond to long-term trend and high frequency intrinsic model are typically represent noise or short-term fluctuations. The middle frequency intrinsic mode functions occupy an ambiguous position in the spectrum, lacking clearly and stable mathematical definitions. Their physical or business meaning frequently remains indeterminate without additional domain-specific analysis, as these components may potentially represent either meaningful cyclic patterns or decomposition artifacts. This interpretational uncertainty is particularly pronounced in applications involving financial markets, climate data, or biological signals, where the boundaries between general signal and noise is inherently blurred. Consequently, post-processing techniques such as statistics significant testing, correlation analysis with known variables, or energy-based thresholding are often required to properly classify these middle frequency intrinsic mode functions and assign them operational meaning. The adaptive noise injection mechanics in Kiden does not improve mode separation compared to early impaired mode decomposition variants, but the methods complete dependencies on data characteristics means the result may vary significantly across different realizations of the same underlying process, necessitating careful sensitivity analysis in practical applications. To illustrate this micro-macro duality, I'll examine two representative techniques, STOS microscopic paradigm approach and Kiden ELM representing the macroscopic approach. The STL model operates at the microscopic level by design. Its power lies in explicitly decomposing time series into physical meaning components, trend, seasonality, and residues, each with statistical interpretable confidence bounds. By computing these non-parameters, trend, surface, and probability bounds as structure pairs, STL achieves remarkable robustness against noise contamination. This deterministic interpretability acts as an archer, ensuring stable forecasting performance even when dealing with sparse or non-stationary data. However, this very strength becomes its limitation. The macroscopic perspective may overlook subtle but critical granular patterns hidden in data. Now contrasted with the Kiden ELM model, which operates at the microscopic resolution through its adaptive noise-assistant decomposition, Kiden hierarchically breaks down signals into intrinsic mode functions, which capture microscale validations patterns that microscope models simply can't resolve. When coupled with extreme learning machines' nonlinear fitting capacity, the model achieves impressive local accuracy. But this power comes at a cost. The implicit stochasticity in both Kiden's decomposition and ELM neural mapping introduce fragility. Without the proper regularization, the model becomes prone to overfitting, particularly in small sample scenarios and facing distributional shifts where microscopic STL would remain unfazed. This composition reveals a fundamental trade-off. Microscopic models provide stability through interpretable constraints, while microscopic models deliver precision through adaptive complexity. Neither approach is universal superior. Their value emerges when they are combined. Admittedly, while no non-stationary data is entirely interpretable or logical deterministic, neither does it represent the opposite extreme of being completely unexplainable or indeterministic. Real-world data often exhibit both deterministic patterns and stochastic fluctuations. Such data components contains that do exhibit interpretable and logical deterministic modularities. Considering micro-level deterministic models and macro-level fluctuations models, each have their merits, therefore needing an integrated approach. Nevertheless, the micro-macro should not imply mutual exclusion. A synergetic framework can be established where micro models and macro models are combined. We have developed a novel methodological framework termed mixture of increasing determinism. The paradigm draws conceptual inspiration from gradual machine learning frameworks. It addresses the inherent structure of sequential temporal data, which typically comprise components exhibiting varied degrees of determinism, ranging from highly predictable or deterministic patterns to highly stochastic or non-deterministic patterns. The architecture of gradual machine learning paradigm is shown as a figure on the right side. Since the gradual machine learning paper uses a classification problem rather than a time series prediction problem as an example, the architecture diagram on the right in the original paper is adapted for classification tasks. However, its underlying principles can be applied to other problems, including time series predictions. The core idea is to progressively extract the most confident patterns and intermediate results through continuous feature modeling and new evidence incorporations, thereby gradually refining the learning representations towards increasingly certainty final patterns. In time series forecasting scenario, the core principle of mixture of increasingly determinacy is to initiate learning from the comparative well-defined deterministic pattern of the components. By leveraging the insights gained from these initial components, the framework progressively expands the scope of interpretable modeling to encompass more uncertainty pattern components, for which can be benefited from previous components constraints with regard to its uncertainty. This iterative target expansion reduces the residual uncertainty associated with the remaining parts of the sequence. Consequently, mixture of increasing determinacy effectively decompose complex problems into more management sub-problems through its pattern divide and conquer strategy. Crucially, each step within this gradual machine learning progression operates on a relative well-understood subdomain, yielding explicit and interpretable intermediate results. This principled approach effectively reduces the risk of overall or at least partial of model data mismatch, such as overfitting or underfitting, by ensuring better alignment between the model's internal mechanics and the specific components of underlying data generation process. Such mismatch are common in less structured learning paradigms where model assumption poorly match the true data distribution. The increasing determinacy is directly derived from the core mechanism. As the framework iteratively identifies and explores increasingly large deterministic components which are amenable to more reliable interpretation and modeling. The remaining stochastic portions of the sequence benefit from the progressive reduction in uncertainty, such as entropy diminishment. Propagated from the results established in previous steps, essentially the resolution of determinism in earlier stages constrains the solution space, leading to a cascading effect of uncertainty reduction throughout the time series data. To know more about the gradual machine learning paradigm, please search the keywords of gradual machine learning on Google Scholar for details. Specifically, consider a concrete modeling example. STL ARIMA provide interpretable deterministic patterns as structured pairs, while micro techniques such as ensemble empirical mode decomposition and deep neural networks characterize intrinsic complex nonlinear models. This collaborates ensemble increasingly determinacy modeling, progressing from micro interpretable patterns to macro complex representations. A straightforward integration strategy involves pre-processing highly violent time series data through anomaly detection or smoothing techniques. These initial steps extract the skeleton structure of the data, what we might call it deterministic backbone, which will be friendly to apply in microscopic models as STL. In this process, while the original time series losses microscopic details, it transforms into what appears as a smooth blue tragedy on our plots. The blue line exhibits minimal amplitude and frequency variations, yet preserves intuitive microscopic progression. When STL subsequently generates both its baseline forecast and its accompanying great confidence boundaries, we establish critical constraints. Any subsequent complex model, no matter how stochastic, must treat this blue tragedy and its confidence envelope as an invariant scaffolding. The microscopic model can further refine the baseline strategy within these predefined boundaries to precisely character subtle latent models underlying the microtrend. An effective refinement approach need not be complex. Just apply the different sequences of red line and regularization to constrain these differences to the blue line's nature, scaled by their local expectations, and then superimpose the normalized differences back onto the blue line can help. This demonstrates the practical performance of our hybrid framework combining Profit for microscopic forecasting and Kiden ELM for micro refinement. While the Profit output blue trend line captures the overall trajectory, it's forced to reconstruct the high amplitude fluctuations indicated within the circled regions. By contrast, the Kiden ELM red line recognizes the high amplitude fluctuations, while its overall position is a little far away from the ground truth. By adjusting the red line's shift to the blue line's position, the refineness successfully identifies these microscale variations and adaptively adjusts this baseline prediction, achieving near ground truth alignment through its hierarchical decomposition capacity. The achieved symmetric mean absolute percentage error, SMAPE, shows a consistent 2% reduction compared to using either Profit or either Kiden ELM independently. The fundamental challenge in time series forecasting lies in confronting the inherent uncertainty or even true stochasticity embedded within temporal data. As evidenced by cutting-edge research, this uncertainty manifests not merely as measurement noise, but as an erodable, eligible property arising from complex system dynamics. In this segment, I will discuss methodological improvements to forecasting mechanics where confronting ever-present uncertainty. First, we should acknowledge the unpredictable factors due to true uncertainty are ambiguous. These two graphs directly depict the utilization patterns of specific type and resource at some time. Modern forecasting mechanics designed to embrace uncertainty focus on jointly modeling to handle mainly two kinds of uncertainty, epistemic uncertainty and aleatory uncertainty. In real-world applications, understanding and distinguishing between epistemic uncertainty and aleatory uncertainty is not just an academic exercise, it's a fundamental requirement for robust decision-making. This distinction does not matter because each type of certainty requires a different response. Understanding and quantifying epistemic and aleatory uncertainty isn't just theoretical. It's an example for making robust real-world decisions. In the context of cloud resource demand forecasting or other sales management business, adding more historical sales data, including promotions, outliers, can reduce epistemic uncertainty. In face of uncertainty, new forecasting mechanics will be helpful. The principle is as follows. We do not expect a predictive algorithm to forecast all problems, but rather to selectively address those aspects they can reliably predict. For the remaining portions, we supplement information through human-machine collaborations, or at the very least, confine the uncertainty with a narrower margin. If we can effectively transform unknown into a known or limited unknown by shrinking its boundaries and reducing its scope, this would constitute a significant advancement. Thank you.
Okay, thank you. Is there any questions? Okay, I can ask one. So in Huawei, can you give us a showcase that how that type of deployment is implemented in your system? Just give example.
Okay. As mentioned before.
Yeah, just a real problem. Yeah.
Yeah. As mentioned before, our the cloud computing itself is a capital-intensive industry and involve a vast variety of resources. And but at the end, the customers can aware of is only the virtual machines. Although this chain is long, we are always beginning at the virtual machine predictions. The virtual machine predictions comprise historical usage and other customers, especially named account customers, declarations. And then we put forward this demand forward to at the beginning to form the delivery chain, where precise operational management is required for each resource.
Okay, thank you. Okay, any questions? Okay, so no more questions. Let's thank the speaker and thank for audience participation. Thank you.